is much smaller than the charging energy, which in this case is about 300 millikelvin. The charge of the island can fluctuate by at most 1 electron. So naturally, it defines the pseudospin 1/2, Q and Q plus E. Similarly, the location of this excess electron, whether it's in the reservoir or on the lead, defines the second pseudospin 1/2, and tunneling events between the reservoirs and the island results in pseudospin flips. And by the virtue of the definition of these pseudospins, the tunneling process is going to entangle these pseudospins and result in an effective antiferromagnetic coupling. Now the pseudospins itself will have some natural energy separation that is tunable with the gate voltage, the plunger gate. And we can go to charge degeneracy and we have a degenerate charge impurity, and under the right conditions you can basically map this Coulomb Hamiltonian onto an anisotropic quantum model. Of course, I'm not gone into any of the details of this mapping in the interest of time, but if you're interested, you can check out this theory paper from Matthew, or I'm also happy to chat more about it. But the reason this is so interesting is now each QPC controls the Kondo coupling of an independent Kondo channel, and hence with a single island you can study the multi-channel Kondo phase transition. So this was done for the first time by Frederick Pierre's group in Paris-Saclay, and they were actually able to fully map out the renormalization group flow in an experiment. So here the axis corresponds to the couplings of the two reservoirs to the single island, parameterized in terms of the conductances. And you see that if you're away from the symmetric line, then depending on whichever reservoir is strongly coupled, it will flow towards the single channel Kondo critical point or the single channel Kondo fixed point. But if you're on the symmetric line, where both the reservoirs are symmetrically coupled, then as you pull the system down, you'll flow towards the two-channel Kondo phase transition, where both the tunnel barriers are renormalized to the ballistic limit. Now in our group, my colleague Winston Baus scaled this up to 2 islands. So now you have a pair of islands, each coupled to a lead as well as coupled to each other. And if you look at the inter-island interaction, it not only involves the pseudospin exchange, but also a charge transfer. And that's because we're talking about charged pseudospins. And if you sit at the triple point of this double dot charge stability diagram, you essentially have a competition of the Kondo screening of each dot with its corresponding lead, as well as an inter-Kondo interaction that's mediated by this term. So you can study this novel critical point by transport measurements, and this forms a very key building block as we aim to scale towards larger arrays, which to get insights into this lattice covariance that's observed in heavy ferrous materials, which are thought to be described as a Kondo lattice model. Now, for any of this to work, we need to be at temperatures that are much lower than the charging energy of the system, which is of course inversely proportional to the island size. As you may notice, these islands are rather huge here, and that's because gallium arsenide forms a Schottky barrier with any metal, and it's very difficult to make smaller ohmic islands on gallium arsenide. But it's long been known that there is this other 3,5 material, indium arsenide, where the Fermi level is spread above the conduction band minima at the surface, and it provides a pathway for making these smaller islands, boosting up the charging energy, and studying these Kondo phase transitions over a broader thermal range. Okay, so what do we really need to get to a metal indium arsenide quantum dot as shown like this? So I mentioned we're working with charged pseudospin. So we really like to work at high magnetic fields that the true spin of the electrons is quenched. And for a straightforward mapping to theory, it's always convenient to work in the low filling factor integer quantum Hall phase in indium arsenide. Next, we want to be able to make these small ohmic islands which have an essentially transparent interface with the quantum Hall edge states in indium arsenide. And we want to be able to tune these interactions via tunnel barriers in a smooth way, because that is going to be our tuning parameter in our simulation platform. Finally, we want to put all of these elements together to make a hybrid metal indium arsenide quantum dot with a large charging energy. So we work with this indium arsenide quantum well that's grown by a molecular beam epitaxy on an indium phosphide substrate. This was done by our collaborators Mike Manfra at Purdue. And since this well is quite deep from the surface, we get a very high mobility. And the density is about 4 to 6 times 10 to the 11, which lets us go into low filling factor quantum Hall with the fields that we have access to in the lab. The way we make ohmic contact is by the way we make these islands is by first etching a trench in the heterostructure and then depositing titanium gold, where we essentially rely on the side wall contact to the 2 ray. And we can characterize the quality of this contact by measuring the reflected and transmitted edge state voltages and fitting it to a Landau vertical model to extract a transparency of more than 99%. Next, let's look at the tunnel barriers. And what we are really aiming for is a smooth control of the outer edge state transmission from the ballistic limit all the way down to pinch off. So this is what we want to get at. And we started out by making this simple conventional point-to-point contacts, pulled it down at 1.5 Kelvin, and at zero field we can see about 8 conductance plateaus. So we see signatures of ballistic transport down to pinch off. But when we pull this down in the dilution fridge and look at it at high fields, we see a lot of features, reproducible features develop on the first riser. And this is also seen in state-of-the-art gallium arsenide QPCs, and it's thought to arise from a small compressible island. It's the Coulomb charging effects of a small compressible island that forms within the construction. So then the question is, can we screen these Coulomb interactions by tuning the confinement potential by maybe adding a third gate? So that's what we ended up trying. We added a third helper gate, and with Schrodinger Poisson simulations, we could already see that even at 0 volts on the middle gate, we can get a much steeper confinement potential. So when we made the device and looked at it at 1.5 Kelvin again, now we see a lot more plateaus, about 16 plateaus at 0 field. And looking at it at high fields in the dilution fridge, we now see smooth risers all the way up to 9 Tesla, after which these Coulomb interactions start to play a role. But overall, by tuning the field and the middle gate voltage, we are able to get to a limit where we can smoothly tune the outer edge state transmission. Now, the final piece of the puzzle is to put it all together to measure these quantum dots. So that's exactly what we've done. We have a slightly smaller island that's making only contact with the indium arsenide two-leg, and we have the quantum point contacts around it to confine the semiconductor region around it. And by tuning the QPCs or the tunnel barriers to the weak tunneling limit, and by sweeping the plunger gate, we can measure the single electron or single charge transitions on the dot. And I would like to point out the strong uniformity we see in the Coulomb peak heights, which is in stark contrast to what you typically see in semiconductor quantum dots. This, of course, has to do with the fact that we're working in the many electron limit, but also we have this metallic island which is screening local inhomogeneities in the electrostatic environment. We can then add a DC bias and measure these Coulomb diamonds. And once again, we see a strong uniformity in the charging energy, which we can extract to be around 95 micro eV. This is already a 4-fold enhancement to the state of the art for metal gallium arsenide quantum dots. So we are moving in the right direction, although there is scope for a lot more improvement in the charging energy boost up. So yeah, now that we have all the building blocks developed, we can put this platform to test by looking at the Hamiltonian that a single island natively realizes. And that's, of course, the Coulomb Hamiltonian with an on-site term, coupling, and the charging energy. Now, this Hamiltonian is not quadratic, so we don't have an analytical solution for the ground state or for conductance through it for arbitrary tunnel couplings. But we can still measure the conductance and compare it to what theory would predict at certain limits. For example, in the weak tunneling limit, when both the QPCs are weakly coupled the island to the reservoir, we see these Coulomb peaks with full charge quantization, and you can fit it to a perturbation theory result to extract an electron temperature of around 39 millikelvin. In the opposite limit, in the strong tunneling limit, when both the QPCs are open almost to the ballistic point, now you can see that the visibility of the charge oscillations has gone down because charge quantization is suppressed. But we still have some theory on strong inelastic co-tunneling, which can help fit these oscillations and quantitatively fit these oscillations and tell us that they are the right, the limit of the Hamiltonian. But we don't need to stop there. We have full independent control of the tunnel barriers, so we can look at charge quantization at any arbitrary tunnel coupling in between these two limits. For example, here I've set the bottom transmission to be 0.6, and I'm sweeping the top transmission. In the ballistic limit, I see no charge quantizations. It's completely flat as a function of the plunger gate. But as the top QPC is closed, you start to develop these Coulomb oscillations with increasing visibility, and you also see some non-monotonicity in the Coulomb peak heights. So this model can thus, our device can thus, simulate the Hamiltonian that it natively realizes, but over an entire range of tunnel values, and we can use it as a test bed for numerical models for the Coulomb Hamiltonian. With With this, I'd like to summarize. So I've spoken about how these hybrid metal semiconductor dots are a scalable platform for simulating the Kondo Lattice model. The indium phosphide provides a way to boost up the charging energy, and we have demonstrated all the building blocks for quantum simulation on a single nanopattern metal indium phosphide dot. We have some ideas for what we can do with this platform. I won't get into all of this in the interest of time, but just talking about a variation of the SSH model that Sam spoke about, where we are talking about these Kondo interactions instead of standard exchange, which is more robust to disorder. With this, I'd like to thank my collaborators, all the work that I've done. My former labmate Connie is an equal contributor, and the material we get it from Microsoft, from Mike Mantra, and Rajiv Rahman and Kim will help with the simulations. Thank you.
All right, thanks very much, Praveen. Are there questions? So with all those electrons running around in the metallic island as well, what are the lifetimes of your pseudo-spin? Is it going to be dramatically shortened by that?
So, all the measurements that we do are transport measurements. So, yeah, as long as you tune the plunger, the state away from the charge frequency, it just stays at a particular charge number, and only depending on how much charge max you have and how close your Fermi level is to the source and drain, you'll have it move from there. So, yeah, we have not characterized the lifetimes per se, but in the transport measurements, we have not run into any issues with that.
All right. Other questions? Well, if not, let's thank Praveen again. And that's the